This video explains how to use the Altair Embed application to control a PMSM motor in an open-loop fashion. We will focus on the PWM configuration and third harmonic injection. For the target, we'll be using the Texas Instruments F28069M launchpad, also known as the Piccolo, the Teknic M 2310P low-voltage servo motor, and a Texas Instruments DRV 8301 inverter board. We'll approach this example using two models, a source model to generate the .out file and a debug model to execute the .out file on the target and write signals back to the host PC in real time. The source model is set up to simulate from 0 to 10 seconds in increments of 0.0001 seconds and to run in real time. The motor control is architected with a main task and a background task. Control right mouse on the motor control compound block reveals this block is executed every 6.67 e to the minus 5 seconds, or 15 kilohertz. Control right mouse on the background task compound block reveals this block is executed every 0.01 seconds and is a background thread, which means it can be interrupted if necessary for the motor control to maintain its 15 kilohertz sample rate. Certain timing must occur during startup to prepare the PWMs in the 8301 inverter. Under blocks nonlinear, the delayed switch block allows you to add a delay to the rising and or falling edge of a binary signal. Startup occurs when the on-off signal is selected on. The startup signal is passed through a rising edge delay of half a second before the PWMs are enabled, and an additional 0.25 seconds before the inverter is enabled. Also, the trip zone input 1 is set to 1. Diving into the motor control block of the source model, there are three PWM signals being produced in open loop. The motor angle, theta command, is set to a ramp signal. The flux command, ID ref, is set to 0, and the torque command, IQ ref, is set to 0.15 amps. An inverse Park followed by an inverse Clark transform are used to convert from the DQ axis system to three-phase. The block labeled third harmonic injection adds the third harmonic to each of the three phases. It is activated dynamically using an on-off input. We'll control this as the motor is running. The open loop control produces three PWM signals labeled PWM-A, PWM-B, and PWM-C. These signals have been converted to 1.16 scaled integer format in the blocks entitled Scale. Within the ePWM block, we are using channel A of the three PWM building blocks. Let's look at the configuration of the first block. There are two basic areas you need to configure in the PWM block, the time base and the action qualifier. Let's first look at the time base setup. The count mode describes how the counter used to trigger the PWM counts. It can count from 0 up to the time base period, abbreviated TBPRD. It can count down from the TBPRD to 0, or it can count up to TBPRD and back down to 0. Believe it or not, the third mode is a good choice for motor control applications because it's easy to synchronize the ADCs that are sensing motor current to sample at the halfway point through the count. So we'll set the count mode to up-down. The timer period is used to define the PWM carrier frequency. A good frequency to use is 15 kilohertz. When the timer period is adjusted, Embed automatically calculates the equivalent carrier frequency. We have adjusted the timer period to 3000 CPU cycles, which produces a 15 kilohertz carrier frequency. Since the CPU speed is 90 megahertz, 3000 CPU cycles equals 30 kilohertz. But since we are using an up-down count mode, the carrier period is twice as long, and the carrier frequency is halved, equaling 15 kilohertz. The action qualifier setup. First, you want to make sure the GPIO pin is set to GPIO 0 in this case. Then the CMPA for ePWMA is set to Z equals nothing, up equals 0, and down equals 1. This means that when the normalized value of the PWM counter, which counts from 0 to 3000 at 15 kilohertz, passes from less than to greater than the duty cycle command, the PWM will be set to 0. And when the PWM counter passes from greater than to less than the duty cycle command, the PWM will be set to 1. We'd like to look at several of the signals from the target as the open loop control is executed. I've wired 7 signals, the theta command value, the measured theta value, an index signal coming from the built-in encoder, and the 3 PWM signals. In addition, I've added the PWM-A signal before the third harmonic injection as the 7th output, so we can compare the signal power in the PWM-A signal with and without third harmonic injection. Let's code gen our source model and see how this works. After selecting the compound block, select Tools, Code Gen. Ensure the Use Selected Compound Edge Pins for Data Exchange is selected. Defaults for the other settings may be used at this time. Select the Compile button. The compile results are presented in a DOS window. Select any key to acknowledge the DOS prompt, then select Quit. Now we're ready to run our code on the target. After loading our debug model, we'll begin with the controller set off and the third harmonic injection set off. After click and go, you'll observe the .out file being transmitted to the target. Then it will begin running. First, I'll turn the motor controller on. The top plot displays the motor angle and the open loop angle command. The lower 3 plots display the PWM sinusoidal waveforms. The quantization is due to the bandwidth limitation of the JTAG interface we're using. On the right, I've calculated the mean value of PWM-A. Then I've shifted the 2 PWM-A signals, one without THI and the other with THI, to have a 0 mean value. The energy of each signal is calculated as the integrated square value, and a power metric value is estimated using a lag filter. Observe that when the THI is off, both power metrics are identical. Now I'll turn on the third harmonic injection. You can clearly see the flattening effect on the peaks of the PWM sinusoids, and a noticeable increase in the power metric.